Hello everyone, my name is Manish Yadav. It's my first video for EMAC 303. Today I'm going to do the classification of PDEs into ellipticals, hyperbolic and parabolic equations. So what are the partial differential equations? These are the function dependent on two or more variable. So let's take a variable a in terms of x and y, like as a function of x and y, d square phi by dx square, plus b as a function of x and y, d square phi by dx dy, plus c as a function of y, x and y, d square phi by dx square is equal to a function which can be x, y, phi dx, d phi by dx, d phi by dy, d phi by dz, or maybe something else. There's a lot of scheme that you can use to describe these PDs, but I'm going to use b square minus 4ac. So if our b square minus 4ac is greater than 0, then it's going to be a hyperbolic equation. And for a hyperbolic equation, we have two real characteristics. If our b square minus 4ac is equals to 0, then it's going to be a parabolic equation. And for our parabolic equation, we just got one real characteristics. And if it's less than 0, then it's going to be elliptical equation, and there's no real characteristics for the elliptical equation. For this class, we used parabolic and elliptical equations. So our parabolic equations are time dependent equations. These are unstudied and depends on the initial and boundary condition, and we can solve parabolic PDEs and by the using finite difference operator. For our elliptical, it's a kind of steady state problems, and these kind of equation totally depends on, like, these kind of problems totally depends on the boundary condition. We can solve these equations by using finite difference matrices method and the Leibniz method. Finite difference method is faster than Leibniz method, and we use this method to solve big matrices, and Leibniz method is used for the small matrices, and it's little slower than the finite difference method. So let's take an example to solve, like, to classify these equations. So I'm going to, okay, so there's the equation d square phi by dx square plus 1 minus x d square phi by dy square, and this is our equation that we did before. So as per this equation, our a term is equal to 1 and our c term is equals to 1 minus x, but there's no b term. So a is 1, b is equals to 0, and c is 1 minus x. If we put these values in our equation, so it's our b term becomes 0, and the rest of the equation is minus 4, 1 minus x. Here the value of x is, like, we can use anything for x. So if we are using the value of x is 1, then this term's going to be 0 and the whole terms become 0, then it's going to be a parabolic equation. If we use the value of x is, like, less than 1, so if we use 0 or maybe minus 1, the whole thing is going to become, this terms is going to be like like less than 1, so less than 0, then it's become elliptical. And if we use this as a greater than 1, so if we use here 2 or maybe 3, then it's going to be a negative value, and if you multiply negative by negative, then it's going to be a positive term which is greater than 0, then it's become hyperbolic. So this, like, this equation is can be in the term of any equation, like it can be in the terms of these three: parabolic, elliptical, and hyperbolic. Let's take another example which might give us some more ideas. So dt by dt, it's like this is our temperature and this is our time, is equals to k d square t by dx square. We used this equation in our class, if you guys remember. Then let's take a road, and so at the initial we have t no temperature, at the final we have like t final. We are going to find like find the temperature in here, like at any point on this road. We are trying to maintain our temperature in this road by using this equation. So as you see, we just got one second order equation, which is our a. There's no b term and there's no c term. If there's no b term and there's no c term, so if I use this value in our equation, our b is going to be 0, 4k, and our c term is also 0, then the whole term becomes 0. It doesn't matter what's our k term, but because our c is 0, the whole terms become 0. Then it's going to be a parabolic equation. And this is also kind of time dependent problem, because there's like function of, we are differentiating time here, so it's also giving a sign of a parabolic equation. Let's take one more example. So here we have some boundary conditions, like our temperature is equals to 10 at the every side. We are trying to find our temperature inside. So in terms of x and y, I use this equation. This is our Laplacian of phi, d square phi by dx square plus d square phi by dy square is equals to 0. So our a term is equals to 1. Then again there is no b term, and our c term is also again 1. So if I use these equations, is if I use these values in our equation, so it's going to, b term is becomes 0, minus 4, 1 and 1, the whole terms become minus 4, which is smaller than 0. So it's a elliptical PDE, and like we got some boundary conditions, there is no initial conditions. It's also give a sign of elliptical PDEs. That's all. Thank you.